Welcome to Math 106, Chapter 6.1, where we are now starting your antiderivatives. So this is kind of just taking your derivative, but going in the reverse. This is called integration. Now, first, let's just warm up with just how to derive this following expression. So to write it all out, I'm going to show you why I'm going to write it out. Like kind of a step-by-step with it, because again, our goal here today is to learn how to go backwards. So with our deriving, right, we bring each one of these down and subtract by 1. So -1, -1. So you have 2 times 4x to the third. That 4 came down, plus, and now that, actually, I'm going to change that color. That was, oops, so sorry, 4. I'm going to change this to 3. I'm a color person, as you guys know. I'm going to change this to 3 x squared minus, we'll just say 1, and then that drops off, right? So altogether, this is 8x cubed plus 6x squared minus 1. And there we're done, right? But let's say we wanted to go in the reverse. So let's say we wanted to do the antiderivative, right? Anti is like the opposite, right? We don't want to derive, we want to go in the opposite direction. So let's say I gave you 8x cubed plus 6x squared minus 1. Now, can you try and go in the reverse? And that is what we're going to be going to do with the bottom portion right here. So when it says anti-differentiation, it's also known as integration. So it's just the reverse of taking your derivative. So let's go ahead and take that derivative that we have here and go in the reverse. So if we have 8x cubed plus 3x squared minus 1. Now, how can we go in reverse? So see if you can pause the video and try just maybe to figure out, right, to go from this step to this step. Well, the first thing to do is to add 1 to your exponents. So step number 1, add 1 to the exponent. Because think about how we do it, right? We come down first and then we subtract 1. So in that reverse order, right, let's add the 1 this time to these values. So let's do +1, +1. And then for your function, or for your term that doesn't have your x value, right? This is now looking to be your constant. We're going to add just your x. So that is your first step. Step number 2 is to, instead of multiplying, right? So we took care of this step. And step number 2, instead of bringing down this numerical value and multiplying, right? The opposite of multiplication is division. So step 2, we are going to divide the coefficient by the new exponent. So if your new exponent, right, is 4 and 3, and we could say 1 if you want, right? But we are going to divide by your new exponent. So we can divide by 4, divide by 3. And if you want, you could say divide by 1. It doesn't really matter here, right? But for here, now that you've divided, so now we get 2x to the 4th plus x cubed minus x, right? Your last thing is to compare, right? So notice that we started with this, right? And we derived, and going backwards, notice that we got all the way to these first 3 units, right? These first 3 terms. So then how do we get this plus 6? Well, we're never going to achieve that plus 6 like right off the bat. We're going to talk about what to do later. But step number 3 is that we add plus c at the end to signify any dropped constant. And there you have it. So this is now your antiderivative. It is your interval. Now we can always include this constant unless it's missing a dx is missing. So typically, right, when we derive, so typically when we say, okay, we're going to take the derivative of f of x, right, we can do that notation. So when we're finished, right, we have that dx to it, right? But when we derive, so typically we want to add c, add plus c to all integrals except if dx is missing. So what I mean by that is here, right? If we are interested in adding that plus c to it, right? I could say, okay, I want to find 3dx. So because this dx is present, we're then going to add that plus c. Now, if it's missing, right, if it doesn't have that notation, then we're not going to be adding that plus c, is what I mean to say from the above. So let's see if you want to get started. You can add, or you can try out these first few just by going backwards. And if you're confident, if you're not confident, just stick with me for the first few, and then we'll make you feel confident in those skills. So let's say we have this notation, and this is just how you say the integral here. That is to say integral. This is the antiderivative. So it's telling us to work backwards, right? So if we're working backwards, right, the first thing we're going to do is if it's your constant, right, or what look like to be your constant, then we add the x value to it on top of 3. And now because, and I just rewrote it here, because I added that dx, I now need to add the plus c. Whereas if it was just asking for the integral of this one, we would just say, okay, this is just 3x and call it a day. Let's do it again. And I'm just going to rewrite the form, x dx. So once more, right, let's add. Step 1 is to add 1 to your exponent. So now we have x squared. Now we can actually let me change that. We said plus 1. So now this is 2, right? Because there was already a 1 here. So now it makes 2. Then we can go ahead and divide by 2. So now we have, now we have 2 over 2 And then because we have that dx, we're going to just say plus c. Whereas if we didn't have that dx from the original case, we have x squared over 2. And now, is there a good way to double check that we actually did this correctly, right? Or maybe these first two correctly? Well, we can take the derivative of 3x plus c. If this is a constant, it's going to drop off and become 0. And if we're deriving this one, right, you can just take off your x. Or the reverse, okay, that one goes away, it's plus 0. And then we can just do exactly what we have been working with all semester. The 2 drops down and we subtract the 1. So this is just 1 and those cancel and you're left with just x. So there's always a good way to double check these. Let's try it again here. All right, we're going to add 1. So this becomes x cubed here. Let's go ahead and divide by 3. So this is now 3 under, and then we can say plus c because there's that dx here. All right, so at this point, let's see if you can try these last 3 that are remaining. Okay, let's add 1, negative 4x squared. We're going to divide by 2 to make this negative 2x squared, and then plus c because of that dx. And again, if we were to go backwards, bring down the 2, that makes negative 4x to the 1. Let's do it again. Plus 1, divide by 9. So this makes x to the 9th. And notice that we don't have to add plus c because it does not have that dx over here. If it wanted it, it would say, hey, the derivative or the integral of 9x to the 8th dx is 9x plus c, or x to the 9th plus c. One more time here. And if you don't like how it's written out, this is the integral of 1/3 x dx. So add the 1, now becomes a 2, divide by 2. So you have 1/3 times 2, x squared plus c because of that dx. So we now have x squared over 6 plus c. And again, you can always double check, bring the 2 down. That would then cancel, make this a 3, and drop 1. Now let's have you guys try one more with the integral of e to the negative 2x. So that is the integration of e to the negative 2x, and let's just add dx to it. So what do you know about the derivative of e? Well, the derivative of e, right, or I should say e to the x, is e to the x. So then how does this apply to the integral? Right, well, first to integrate, right, it is just working backwards. So first we have to write itself. So step number 1 is to actually go ahead and write itself. So step number 1, write itself. So that is e to the negative 2x. And then keep in mind what we know about the chain rule, right? We typically, when we derive it, we say, okay, this is negative 2. But to go backwards, we now have to, instead of multiply by it, we now have to divide by k. Keep in mind, this is k here. So we're going to divide by -2. Therefore, we have -1/2 e to the -2x. And then we'll just say +3 because I added that dx on top of it. Now, if you wanted to work backwards, we write itself, and then this drops down, makes it a +2/2. We can cancel, and you're left with itself. So that's why your integral of e kind of looks very similar. Keep in mind what you know. You are just working backwards, right, with what we typically have. So it says, suppose that f of x is a function whose antiderivatives are f of x, so that is your integral, plus c. The standard way to express this fact is given by, so this is the notation of your integral. This is the integral notation. And then this is your actual integration response. So this is the response, where f of x, the big f of x, is your final product. And then we say +3. This symbol here is called your integration sign. And the entire notation of that integration is called the indefinite integral and stands for the antiderivative of your function. So if we were to go with the reverse of your power, exponential, and logarithmic rule, right? Well, your power rule, right, that we've been working with from that last page, we had x to the r dx. How would you, what did we do, right? We said step 1 was to do what? We said add +1 to the exponent. Perfect. So we can write x to the r, and we'll say +1. And then step 2, we said to do what? Well, step 2, we said to now divide by the new exponent. So your new exponent should be written as r +1. So we have divided by r +1, where in the denominator here, we're just going to say, because now they have a denominator, we do not want r to be equal to -1, otherwise we're going to cause an issue. And then step 3, we said add c. So this is your power rule, really just written out in a very standard response. So can we do the same thing with your exponential rule? So the rule that we just covered, we said e to the kx dx. How would you write that out? We said, okay, well, step 1 was write itself. Actually, let me use a different color for that. So step 1, write itself. E to the kx. Step number 2, what did we do? Well, we said we're going to divide by k. So divide this time by k. And the last thing we need to do, step 3, is add +c. And again, we have something in the denominator, so we want to make sure that we specify that k is not equal to 0 here. Now, can you come up with a rule, because we haven't seen it yet, can you come up with a rule for 1/x dx? Well, it kind of gives it away, right? The logarithmic rule, right? The logarithmic rule or the log rule is that if we see 1 over x or 1 over a value, we are really taking the derivative, or we had taken the derivative of ln. So if we're working backwards, we write natural log, and we're going to use the absolute value sign here of x. That is because we talked about, hey, values of x for your natural log, we cannot be equal to 0 because there's an asymptote, a vertical asymptote at x is equal to 0. And again, no negatives because your graph here of natural log had no negatives and no zeros. So that's why we're going to write the the absolute value sign. And then step 2 is that we get to add plus c. So it's the ln of whatever that is on the bottom, and then plus c here. So those are the 3 rules that we're going to be seeing. Everything else should remain the same. So see if you can try out example 3. So we have the square root of x. Now, just like you did last time, you definitely want to show the power of x, that is 1/2. So step 1, we said, okay, add 1. So that's 2 over 2. So now we have x to the 3 over 2. Then we will divide by 3 over 2 and add c. Then we need to clean it up ever so slightly, right? Keep, change, flip. That just means that we are going to flip this upside down and multiply. So you're left with 2/3 x to the 3 over 2 plus c. And again, to check that that is the case, all you have to do is bring this down, 3 over 2. Those end up canceling. And then subtract 1. You'll get 1/2. Let's do it again over here. We have 1 over x. So we now get to say, okay, this is ln of x. Actually, let me try that out one more time. Ln absolute value of x, and then plus 1. Again, if you want, you can show the power, right? This is x to the negative first power, right? Because we are working backwards, anytime that you have a power or a degree of -1, this means that ln was used. And so for here with the absolute value of x, we actually have those 2 solutions here, which you might not see it right away. For me, this is all I am looking for, but in the future, you might have teachers that want you to show it out what it actually means. So one response is that you could have something like this when x is, and actually in this notation, we could say when x is greater than 0, say positive number. Or we could write it out where we have that negative x here plus c, but for when x is negative, it compounded with the double negative here to make positive. What I'm looking for is really this. If for me, you're not using the absolute value signs, you'll notice that later on, I'm going to be dropping that absolute value sign. That is perfectly fine for my class. So what do we have here? Well, if we were to show your power, right, this is the integral of -2 dx. -2, right? Well, yes, it's located in the denominator and it looks negative and it looks like we might have to use ln. This is not the correct power here. Instead, we do plus 1. So that would be x cubed. And now we divide by 3. And then we add c. So we have x cubed over 3 plus c. And again, try, actually plus, I'm so sorry. I said plus 1 and this, I said plus 1 and then I notice how easy that is to kind of get those values mixed up. Actually, I'm kind of glad that I did that to show you that it is really easy if you're not going back to check, right? But -2 plus 1, that will make -1. There we go. -1. And therefore, we're dividing by a -1 here. So all in all, this is a negative over here. I'm going to write it one more time and have this drop. So it's -1 over x plus c. That is what I'm looking for. And again, I want to very clearly emphasize here that x is not equal to 0. Now let's take a look at some other basic properties of integrals that you're going to be coming up to see. Is that we have something called that sum rule, where we said, okay, if we have the integral of f plus g of x, right? So multiple terms, what we can do is just integrate them separately. Just like you derived them separately, we can integrate them separately. So that's one of them. And another one is that if you have any sort of coefficient on the outside, that is not going to affect the overall integration process of it. It will affect the answer at the very end. But in the meantime, what you can do is put k on the outside of your integral and derive as you normally would, not derive, integrate as you normally would. And then you can bring back your coefficient to simplify. Could say coefficient is in the way only use, I'm so sorry, y'all. Used to simplify. So sorry, I have a very needy cat that's next to me. So let's have you guys try out example 4. So let's go ahead and integrate these in just separate actions. So we have the integral of x to the -3 dx plus the integral of 7e to the 5x plus the integral of, and I'm going to show the power here, so I'm going to bring that up, 4x to the -1st dx. So now let's go ahead and try out some of your rules. We said, okay, we're going to add 1 and then divide by 3, or -3 plus 1, that makes a -2 here. So we have -1 over 2 x to the -2. And if you want, you can say plus c, but notice that we're going to have a lot of these dx's. That doesn't mean that it's plus c plus c plus c, so we'll have plus 3c. No, that's not how it works. We're just going to include 1 plus c at the very, very end. So I'm just going to drop that. You also have this 7 here. So if you want, you can bring that 7 on the outside and erase. So now you can go ahead and integrate. So that 7 is going to go over here. You can say plus. Actually, let me keep my colors the same. So now we have e to the 5x, right? We said, hey, keep that the same. And now divide by k. So divide by 5. And again, if you want to, you could say plus c, but we're going to wait and hold off for that plus c. And notice how the 7 is not affecting the overall integral of it. Now next, right, we have, we have this 4 that we can go ahead and bring out over here. That's not going to affect our integral, so we can have 4 on the outside. And now when we look at x to the negative first power, right, if it's to the power of -1, that means we used ln. So we have ln, the absolute value of our x. And at the very end, we can say now is where we put your plus c. So let's go ahead and clean up just ever so slightly. We have -1/2 over x squared plus 7/5 e to the 5x plus 4 ln of x plus c. So there is our final response. So now let's find the function f of x for which we have your first derivative. And then we want to go ahead and they're going to give us a value where we said this is a point on your graph, right? This is the point when x is 1 and y is 4/3. This can help us find this particular c value. So let's start by just integrating the following. So first, find the integral of x squared minus 2 dx. So for us, we are going to add 1 and divide by 3. So we have 1/3 x to the 3rd minus 2x, and we're just going to add the x, and then plus c. So this is your integral. We'll call this big F of x. And now if we're given your point here, 1 and 4/3, it can help us find your plus c. We need to find your constant. So after you integrate, so step 1, integrate. So kind of work backwards. Step 2, we're going to plug in your point. We know that x is equal to 1 and y, which is f of x, or in our case, big F of x, is equal to 4/3. So let's go ahead and do that part. We have 4/3 is equal to 1/3 times 1 cubed minus 2 times 1, and then you still have your plus c. So go ahead and solve for c here. So we have 4/3 is equal to 1/3 minus, and I'm just going to put this over 1. Common denominator here is a 3, so 6/3. Again, your plus 3. 4/3 is equal to -5/3 plus c. So let's go ahead and add those two together. So we have 9/3, or 3 is equal to c. So if we were to put it all together, that's your last step. Plug in c into f of x. So if f of x is equal to 1/3 x cubed minus 2x, and this time we can say with confidence plus 3. Now the reason why we know it's 3 is because we are given a specific point. So let's say this is some sort of function, right? There are several different options based on the points that can come up on a particular graph. So for us, we found one where we had the constant, your constant, that was a 3. Whereas if we chose a 4, that is going to shift your y-intercept up, because your constant is your y-intercept, right? It doesn't have anything to do with your x value. Whereas if you chose a different y-intercept, it could be at 2 or at 1 or at 0, and you have lots of different values of c. So unless you're given a point, that we are confident in, we will not know what C is. So if I give you a point in the future, which I do really like this problem, because it kind of gives you the extra step of how to find that C, is that it kind of puts it all together. Now we have one more page and we have a very quick example. So these are kind of some extra examples for you guys. So kind of take what you need. Example 6 says a rocket is fired vertically into the air. Its velocity at t seconds after liftoff is v of t is equal to 6t plus 0.5 meters per second. Before launch, the top of the rocket is 8 meters above the launch pad. Find the height of the rocket measured from the top of the rocket to the launch pad at t time. So we have, first off, your velocity. We have v of t is equal to 6t plus, we said, 0.5. So velocity, right? We said velocity is the first derivative of your positional function. Position. And this is velocity. So now if we work backwards to integrate, we can go ahead and get your positional function. So we can go ahead and find the position if we take the integral of such, and I'm going to say d of t. I'm going to use dt here because the other ones were all in terms of x, so I've been using dx, but whatever value, whatever variable that you're trying to integrate is just dt, kind of like we did with like d over dx, that sort of thing. So we can add 1 and then divide by 2 here. And here we just get to add, not an x, but a t. So here we have 3t squared plus 0.5t. And then we can say plus c. Now this is your position function. Now we need to figure out, okay, well, what is C? It says find the height of the rocket from the top of the rocket to the launch pad at t time. So before this thing has even launched, we need to figure out, well, what time, what height are we at? It is looking at, right, your initial height. This is your y-intercept, your initial height. Did they tell us what your initial height was? Well, they said before launch, the top of the rocket is 8 meters above the launch pad. That is us saying that this is before launch, when t is equal to 0, we have the value of 8. So overall, your function is 3t squared plus 0.5t plus your 8. And there you have it. There is your height of the rocket from the top of the rocket to the launch pad at t time. We do not know your t, and that's why we have it listed here. Let's try it again with example 7. It says a company's marginal cost function is c prime of x is equal to the following, where x denotes the number of units produced in one day. The company has fixed cost of $1,000 per day. Find the cost of producing x units per day. So we are given your marginal cost, and we want to know what your overall cost is. So we need to find CX. So we need to integrate, right? Because this is marginal cost. We need to work backwards to get to C of X. So we now need to integrate. So we need to integrate 0.15x squared minus 2x plus 80. So here, right, let's work on your integration. We do plus 1, and adding your x. This one we divide by 3, divide by 2. And if you want, you can divide by 1 on that last one. We have 0.15 over 3 x cubed minus x squared plus 80x. And then we can say plus c. And I'm going to do dx. There we go. I was missing that. Now, this is your cost here. Now we have lots of variable costs, but now we need to figure out your plus c. Keep in mind, this is your initial cost, right? And in terms of your context, instead of saying, okay, this was your initial height, this is now your initial cost, this is cost no matter what happens, right? What is that called? No matter what happens, you're going to be hit with this bill. This is your fixed cost. Your fixed cost, they said, was what? Well, your fixed cost is 1,000 units a day. So overall, we have 0.05x cubed minus x squared plus 80x plus your 1,000 in fixed cost. This is your cost function. Now, if we went on to ask, hey, if the current production level is 30 units, determine the amount that cost will rise if the production level is raised to 60. So we need to find the difference between the 30 and the 60, given that we have this as your new function. So I'm going to paste here. And one more time, I'm going to paste right here. So 30 and 60. I'm going to just rewrite that one. Go. Let me move these over, add some things. I'm just being lazy today. I don't feel like writing so much out. Arguably, I'm making maybe more work for myself, but who knows? So we said 30 and 60. So we got 30, 30, and 30, 60, 60, and 60. Let me go ahead and move that just a little bit closer. Again, just a smidge closer. So let's go ahead and put this into your calculators. So we have 0.05 times 30, that is cubed, minus 30 squared plus 80 times 30 plus 1,000. And let me just double check that I wrote that all right. All right, so we have 3,850. And if we change that to a 60, and this to a 60, and this to a 60, we have 13,000. So let's go ahead and write those in. We said 3,850 and 13,000. And if we want to determine how much costs will rise over that time, we are looking for the difference between the two. $13,000 minus 3,850. That would be 9,150. And there you go. So hopefully that kind of basic intro to integration, you feel a little bit better, and how to find C as well.